Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about power generators. So let's dive right into it. Now, we all know that we need electricity in all every day-to-day life, but here's the needs are different. Not every generator would be built with exact same specification. For example, you may have a requirement that this generator is supposed to be working for 24 into 7 into 365 into 10 years. Only then, and at that point also, all we're gonna do is re-maintain it. We're not gonna stop it. It's just like, okay, maintain it. Is all the bearings good? All the things that are consumable, insulation and all that jazz, are they good? Good, go back to work. So that's a different requirement. Then you will have something that has to be adaptable. For example, hydropower plants. Again, the generator still has the same kind of requirement, but it has to handle much larger variability into its output. So you have to manage that. And some scenarios you will have something small and powerful, not because like it's supposed to run 24 into 7, but it's supposed to be like, hey, for a small duration, let's say 4 or 5 hours, this puppy should start working, and then it should continue for a few hours. And then you have another reality of things is that it has to be low cost. In some scenarios it's okay to spend a lot to get the best of the best. In some scenarios it's not, because you might be like, this generator is the best out there, but it costs $1 billion. People are like, yeah, no thank you. So that's the reality of it. Engineering is just about balancing that, and finding the right tool for the right job is compulsory. So let's understand the logics behind it. Now, whenever you start to look for generators, alternators, even for personal home emergency use, or you want to understand what goes into power plant, you'll find a lot of words. Now, one of the words that you will find most often time would be synchronous system. Now, what does that mean? That simply means the ideal scenario. Basically, if the rotor is here and the energy should be created here, so that will create because it's a rotating thing, it should create a RPM and a frequency into the system. Now, if that is completely synced, basically where it's supposed to be and how close it really is, if those are very close and very reliably close, then that will be called a synchronous system. Think of it this way: when you have induction motor, all the water pumps generally, and if you put a lot of load into it, the RPM goes down. Now, synchronous, if it was a synchronous AC motor, that will not happen. What will happen in synchronous system is that simply either it will stop working or burn out. It will not allow you to change the RPM. So synchronous are like that. Now, why people want to build synchronous? Why do they not want the idea of give, like, be more flexible? Yes, in some scenario that flexibility is desirable, in other scenario is not. So having a synchronous system allows you good control. So when you're talking about generator, not motors, when you're talking about generator, you want control. You're like, no, I want 60 hertz. That means I want 60 hertz. There is no a bit more, a bit less. No, it has to be exactly like that. So synchronous allow for good control. Now, in some scenarios you may want asynchronous system. Now, why would you want that? Asynchronous system is but more sloppy. Now, that could be desirable trait. Like, for example, in some scenarios you may be like, hey, I want a system that only works when it when there is a power to it. So people will like asynchronous system, because even if the RPM is higher, it will only create what is externally controlled. So wind turbines could really enjoy that. Small hydropower plant would enjoy that. So not every place you want like good absolute control, because that means you have to have a controller there. In some scenarios, you're like, hey, give me something sloppy that just works, but it's it's a bit more flexible. Then you will have two core components: brushed or brushless. Now, brushed system, we know for a fact, like, in motors is like brush not good, brushless better. But in generator it's kind of a bit different, and like, again, it's the same logic, is that can you afford to go brushless or not? And then you will have two core components, and this is one of the most frustrating thing I found about internet, is like there are two core designs. Basically, are you rotating the magnetic field or are you rotating the generator? Now, like, wait a minute, how the heck you can rotate a generator? I mean, like, from electrical point of view, if you have an armature, basically stator, and you're rotating magnet inside it, that will be called rotating field. You are rotating the field. But what you'll have, the electromagnet is on the outside, and inside you're rotating the quote-unquote generator part of it, the armature part of it, the part that is generating electricity. It will be called rotating armature type. Now, these are the two core types. Most generator you will see will fall either one or the other. That's it. That's all you're gonna get. Now, most of the time, people, that the moment you type rotating armature design, people are like, how rotating field is much better. While that's absolutely true, but I never understood why the heck rotating armature design is so prevalent in India. My assumption at this point in time, looking into this system, is that it resembles basically motor system way too closely. So basically, if you are a company and you can manufacture good, let's say, induction motor, 3-phase induction motor, or let's say slip ring induction motor, that's more or less what you need for generator. So I'm pretty sure that's why at low budget you can find rotating armature designs, because while it does have hundreds of flaws, it is super easy to mass produce, and that's why I specified cost plays a very important role. Rotating field, yeah, the moment you are talking about some big boys, of course it's gonna be a rotating field system. Then you could have a weird scenario where you want motor and generator combo unit. For example, in your car you have a starter, that's like a motor system, and then you have an alternator, that's again a generator system. Now these two are completely separate. We are always think about them as a separate system. There are always two separate things in a car, but realistically speaking, that's not necessary, because everything that is a good motor can also become a good generator. And I mean, really, like you can literally have a 3-phase induction motor. Do not tamper anything with it. It's like, I don't get it. It's like, why the heck everybody buys an induction motor and the first thing they do is like remove the core, put magnets into that. If you want to do that, just buy a brushless motor. And if you want to use induction motor as a generator, which mind you, you can buy generator set that utilize that. All you have to do is add capacitor to its output winding. That's it. That's all you need to do. Like, that's how generators are made, real life generators. So you can buy that, and I have provided video down below where you can see people are converting normal. And I don't mean when converting is like that going inside the system. They are just like, here's a capacitor bank in delta section. Of course, those capacitors have to be run capacitor and high voltage, as in like if you are talking about 200 volts, so people will generally urge you to buy capacitors that are 300 or 400 volt and run capacitor, meaning they can be on all the time without going boom. So you can just have that induction motor, which is a really good motor, can also become a really good generator as long as you are able to exceed its RPM. Basically, if basically on the nameplate it will say run at 1500 RPM, you start to exceed that RPM, basically your prime mover starts to move it at, let's say, 1600, it will become a generator. So you can have a scenario where you need motor and generator, and many modern F1 started to introduce in, like, large swaths of public, whereas like turbocharger was actually acting as an energy recovery system. It's like, what if you want to go around a curve but your engine is already revved up and you do not want boost to be too high? It's like, okay, put a load on the turbo side of it, so it will directly extract energy from exhaust and it will charge up the battery. When you are like on the streets, you want YOLO power, it will act as a motor going boost. And then same can be done with basically every single electric car has that. It's like, that primary motor that's moving your car can also act as a generator. So many times you may have that requirement, and if done correctly, almost every design, other than some few cases, most motor from BLDC to AC induction to whatever have you, especially if it has magnets, then it's super easy. It can act as a motor and generator. And if you buy Rolls-Royce cars, you would notice that most of the newer ones have that small level hybrid system. They already have that motor and generator. So we are reaching a point where we'll no longer have independent motor and independent generator in our cars. We'll have just one combined unit. Heck, my dad's scooty has that. It has that BLDC motor system, which is acting as a alternator when it's like, engine is running, and a starter when he wants to start the system. So that's something that has already been achieved, and if you pay attention to it, you will find out, like, especially newer luxury cars that have 48 volt system have that. Now, one word that will always come along is prime mover. Hold on. So prime mover is another aspect that you will always find. The moment you start to research generator, you're like, prime mover. What does that mean? That simply means something that is applying the energy from the outside. For example, in wind turbine, the wind is the prime mover utilizing the blade. So blade will, for your generator point of view, the blades are the prime mover. In case of water, the water is moving the turbine will become the prime mover for your generator. And that's why I specified induction motor are generator. You can see that. That's how it's utilized. And because it's asynchronous and sloppy, you can directly connect that puppy to the grid. I did not even knew that. That's how it's utilized already in the world. So you have to understand prime mover first, because every prime mover will have its unique signature, meaning some prime movers are like, I'm fixed, I'm constant, I'm immovable. Awesome. So you will have a different generator selection for that. Some movers are like, I'm a bit more flexible. Some would be like, I'm YOLO flexible. So you need different generators. The generator that will work for hydro will not work for wind. What will work for wind will not work for steam turbine. So that's the reality of it. Prime mover has to be your first selection. So if you are building your own generator unit, you have to sit down and be like, what the hell do I want? Like, how my prime mover behaves. Like, heck, that will also directly control the geometry of your system. For example, you have a petrol engine, you will buy something, let's say, that has only 2 poles. Why? Your petrol engines generally have higher RPM. So if you want to produce 50 hertz electricity, you need 3000 RPM. So if you have petrol, generally that's a good RPM. But what if you are talking about diesel system, that is lower RPM one, 4 poles as needed, because that's 1500 RPM. But what if you're like, hey, I want to use induction motor as a generator, but my RPM is not high, you will go for 6 pole. That's only requires you to have 1000, exceed 1000 RPM, or 8 poles, 750. And that's why you will notice very large diameter motors. Generally, that's the reason. The more poles you add, the lower the RPM becomes. And you will like, generally there are 3 types of generation system: 50 hertz for India, 60 hertz for USA, and 400 hertz for aircrafts. And you were like, why the heck aeroplanes, commercial jets, fighter jets use 400 hertz? Well, reality is the higher the frequency, the smaller your transformer, smaller your motors, those sort of things, but also your generator. So basically, higher frequency does allow some benefits. So people use that. So that's the whole point. Your RPM and stability will define what kind of generator you use. For example, wind turbines, because the RPM is YOLO on there, people have to use what we call doubly fed induction motor. Specified inductions are sloppy. They utilize that aspect to it. If you put synchronous generator there, good luck. So that's the reality of it. And more poles generally means lower RPM. So it's up to you. And it will translate to even 60 hertz. So if you're like, hey, my engine can only rev up to, let's say, 1200 RPM, go with 6-pole system. If you're like, hey, it's a slow watt system, it's an old diesel generator, 900 RPM, go with 8-pole. So you can easily find this basically RPM to hertz system anywhere. That's the whole point of prime mover. You have to understand the prime mover first before you buy anything else. Now, in motor system, you always want to go with brushless because brushes wear down and you do not want anything wearing down. So in generator industry, this is also a normal thing. So how we achieve that? Well, reality is you need what we call relative motion on magnetic lines through a conductor. That's all you need, and it has to be relative. It does not mean like you can have magnet and conductor moving together, it will not do anything. You need relative, basically going like this or like this. You can have static magnetic field, move the conductor, it will still work. You can have static conductors, move the magnetic field, it will work, or whatever have you. So generally allowing it to go round and round allows you to have better generator. You can have linear generators, we have that torch that you have to shake, so you can have that, but reality is you need electromagnet or magnet generally. Now you may be like, why the heck we don't use magnets in generators? Well, reality is magnets that can provide the power needed would be too expensive, too big, and very difficult. Now what does that difficult part mean? Difficult part means, think of this way, like for European trains, once they actually wanted to go very high speed, as in like trying to achieve 600 km/h, now not for service speed but for world record, they used magnetic motors. Basically workers who had to install that motor into the bogies, they were very frustrated by that because tools were getting stuck into that. So yes, there are now modern neodymium magnets that are high temperature resistant and powerful enough to do the job, but here's the deal: they are idiotically expensive. And on top of that, if you are talking about a generator that you, let's say you buy today and you want to keep using them for, let's say, 10 years, they will lose their power. Magnets lose their power like roughly specified 1% per year. Now again, 1% does not sound that bad, but here's the 1% of 100% is 1%, 1% of 99% is a bit more, 1% of 98% is even more. So you get that point. It's a compounding loss. Again, it won't translate to a much, but again, if you're paying for energy, you want to be damn sure. So people generally want to use electromagnet, and it also gives them a control factor. That's a desirable thing. You want to control the output. So generally we'll have DC dump coils. Now what does this puppy do? This is just a coil around the main rotor, and this is gonna you're gonna energize this puppy with a DC current, either from power supply or from battery, whatever have you. Now this puppy will create a magnetic field. Because you have a prime mover diesel generator that is rotating the damn thing, you are inducing current into the system. Awesome. Now that is AC, unfortunately. Now electromagnet does not like AC. Electromagnet likes DC. So you may be like, okay, I was introducing DC. How the heck it became AC? Because of rotation. That's the whole point. You have to understand this is rotating. That's how we get sinusoidal waveform. You are rotating, you can send DC, it will become AC just by the fact of induction and rotation. So that AC, you get that. Okay, now you have to solve the issue of brush. You have dumped energy into the system without requiring brush. That's awesome. After that, you have to send it through what we call diode rectifier stage, basically to make the AC into DC. Now once you do that, that DC will be fed into the main rotor, and now main rotor will act as a electromagnet. At that point in time, you have a generator. You have a basically quote-unquote magnet rotating inside a stator. Stator will have amateur windings around it, and that winding you will tap off for electricity. So it works. Now DC feed will allow you to control the system. For example, let's say your generator starts to go YOLO on power. You started the system, generator is like going YOLO high RPM, but you don't have load on it. You want to be like, hey, calm down, man, calm down, relax, calm down. So you will control the what we call excitation current, basically the core current. You're like, hey, let's calm it down a bit. So DC excitation that you were sending, you will try to calm it down. So that gives you a feedback control. Basically you can monitor the voltage, and that's why all these system, brushless generator system, utilize what we call AVR, automatic voltage regulation. So it will directly basically study what's coming out of the generator section, and based on that it will do modification to the DC that is being sent into the system. So it's like, hey, voltage is going up because there is no load. It will be like, okay, let's calm down the exciter current. Now after that point, let's say you put some load and the voltage starts to sag. It's like, whoa, voltage is going down, let's pump up the system. So that's why you can have brushless system, and you want to use this system rather than having permanent magnet, because in permanent magnet you will not have this kind of control. And you may like, what if I increase the RPM? Your frequency will change. So that's an undesirable effect. So that's why people want to have this sort of system rather than having permanent magnet. So this is a brushless system. And again, if you watch my recent video about magnetless motor, exact same thing. That's why I specified almost every geometry that we have, every topology we have is almost motor and generator at the same time. And I'm pretty sure somebody can figure out how to make it as a good motor also. And some are, I'm pretty sure some are where this acts as a starter motor. Then we come to power plant. Now power plant is basically big. So what does that mean? That simply means power plant utilizes brushes. Now I'm like, why the heck you want to have something that has friction, inherently friction? Like everything wants to be brushless. We use brushless DC motor. We love induction motors. Synchronous motors don't have anything that resembles a brush. So why the hell something as important as power plants utilize something that has brushes? Now best understanding I can come up to, I'm not sure, this may be wrong, is that induction, basically having the induction coil dumping energy into the rotor, have some losses. You can never gonna have 100% transfer. Physics does not allow that. So you will, let's say, have a 2 or 4% loss, and then you will have diode bridge also. Diode also acts as a resistor, so that's also losing a bit of energy. So you could have a very high energy loss. Yes, this exciter current is almost nowhere near big percentage of the main generator output. So main generator output could be, let's say, 100 megawatt. This will barely see 10 megawatt. But here's the deal: even if it's saying 1 megawatt, 1 or 2% of 1 megawatt is lot of energy. So for that reason, people may simply say like, okay, losses from brushes is far more desirable, because again, rather than having 2-step loss, we can just have 1-step loss. So that's the best understanding I can come up with. That's why all power plant generators are generally brushed. Then we come to how the heck these puppies are operated. What's the unique thing about them? Well, generally on the stator side, basically things that are giving you the energy, they have hollow tubes in them. Basically the conductor is hollow tubes. They're generally at lower megawatts, as in like 4 or 5, there are rods, and higher megawatts, as in like 100 megawatts, 600 megawatts, they are hollow tubes. Now like, why the heck it's hollow? Well, it is hollow so water can flow through that. The moment you start to talk about that kind of energy density, where you are talking about 100 megawatt to 200 megawatt to something even bonkers than that, the waste heat at 99% efficiency is so goddamn high, it will melt anything. So you have to use liquid water directly flowing through the stator coils to cool it. Without it, it will simply melt. There is no discussion here. You have to have good cooling. Then we come to the rotor part. Again, this is also an electromagnet. How the heck you want to keep this cool? And you have megawatts of energy going into it. So what people utilize is hydrogen. Now like, wait a minute, hydrogen, why? Well, hydrogen is the lightest gas. What does that mean? That simply means at any given temperature, it has the highest movement speed, meaning you have a hot surface. Hydrogen collides with it, it moves at much higher velocity, it creates much more turbulence, it extracts more energy from the hot surface, so it cools it down. So how do you cool the hydrogen? Well, in the rotor casing, basically everything that is encased in the system, there will be radiators that are water cooled, and hydrogen is basically taking the heat away from the rotor and dumping into the radiator. Radiator is good enough to take the heat away, and basically that radiator is being coupled to this core without any physical connection, utilizing hydrogen as a intermediary step. So hydrogen generally inside the system is around 50 psi to 60 psi, or sometimes even higher psi, but you do not want too high psi, because the bearing seals that you have to have, that has to be even higher pressure than hydrogen pressure inside. So hydrogen is completely locked in there. And yes, we had accidents where hydrogen seal broke and boom happened. So that's a serious hazard that you have to be mindful of that. So people do take a serious precaution on that. But hydrogen does allow to us to make very cool basically small rotors, and the only way we can make even denser equipments is just go to superconductors. And utilizing brushes on this, basically utilizing electromagnet, not permanent magnet, we have controls. Now control in our national grid, any national grid, basically be it European national grid, be it American national grid, Indian national grid, Pakistani national grid, Nepalian national grid, all those are controlled by RPM. Basically the frequency is locked and it must not drift, because every single rotor is connected to every other rotor, and I'm talking big ones, not small generator ones, I'm talking big ones. Anything that's, let's say, 50 megawatts or up generally is connected to the grid, and it's a hard coupling. Because it's a synchronous system, it's a hard coupling. So this is how we stabilize our grid. These are the buffer of our grid system. Like, how the heck generator is a buffer? Well, generator is a massive thing that's rotating, coupled to a even bigger turbine. The turbine could be around 400 tons or even 4,000 tons. So you have giant mass that is spinning at high RPM. So this is a two-pole system, so it must be rotating at, let's say, 3000 RPM. So 3000 RPM moving at like a 40 ton to 500 ton object, rotating at that speed will not change the speed. No matter what you do, it will not change the speed. So you put a lot of electrical load. Let's say you turn on your induction furnace for, let's say, a power plant, basically metal furnacing plant, it will still not slow it down. Now again, it will start to slow it down. The inertia will keep it that initial jolt, but it will start to slow down. The slowdown would be enough for a computer to detect is, hey, that's slowing down. Then it will talk to the governor, basically steam valves. It's like, hey, can you open the steam valve, because this puppy is starting to slow down, let's speed it up. So that's how the frequency is maintained. 50 hertz is 50 hertz, it's never gonna drift. Now in olden days, as in like, in early 80s, 1980s and all that jazz, we used to have like, frequency was like 50 hertz or 51 hertz. Hey, slow down, slow down. Okay, 49, too slow, we give it 50. Nowadays it's like 50 hertz dot 001. 49.00 is like very close. We are very precise nowadays. So that's how we control the RPM. Now that's another issue. It's like, how else would you control the voltage? It's like you are controlling the RPM and that is giving you the frequency control. How the heck you going to control the voltage? Utilizing the core power. It's like, okay, load has been disconnected. Let's say it's evening, people are shutting down their offices and all that jazz. The load goes down, your RPM starts to pull up. Now you're like, okay, governor, chill down, cut the steam flow. Okay, RPM stabilized, but voltage still has stacked because there is no load on this puppy. So you will cut the core. Basically you are seeing the electromagnet, this electromagnet part. It's like, hey, calm down. That's awesome. And then you can have invert of that. It's like somebody turned on some very huge event, or Indian cricket match is happening. It's like, okay, crank that puppy up. So that's why we want this two core factor control. And I do not see any feature where somebody will put electromagnets here, basically permanent magnet here. You can do that, it will work, but again, if you want to trust a magnet in high temperature environment, they don't last very long. And on top of that, you lose a control factor. You always want control factor for stability of the grid. So that's how power plant works. And they are a surprisingly marvelous piece of engineering. I have provided a detailed construction video of an actual generator that is in actual power plant. I randomly found it, so please do check it out. It's quite amazing. So this is how power plants operate. So this was my presentation on power generators. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me express disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.